Welcome to GenAI Research Insight Hub channel. In this video, we build the GenAI Pocket-TTS app powered by Pocket-TTS. It's a lightweight, high-quality text-to-speech model that can run directly on your device. Let's get started. To GenAI Kit Voice Synthesis Engine. This builds an AI text-to-speech service. The API supports multiple pre-built voices, like different speakers. A user can choose a voice and send text, and the system generates speech in that voice. The audio is returned directly as a WAV file, which can be played in a browser, mobile app, or downloaded.
The moon forgot her name one quiet night and drifted dim and uncertain.
The system also supports voice cloning. Instead of choosing a predefined voice, a user can upload a short audio sample of a real person.
Someone else was doing bigger, bolder, brighter, but not necessarily better. If you have 10 windows, I'll have 12. But we forgot to ask what
The AI analyzes that voice and then speaks the new text in the same style and tone. This allows the system to mimic real voices, accents, and speaking patterns.
one quiet night and drifted dim and uncertain above the hills. The stars noticed, first one by one, they leaned closer and whispered memories of tides pulled, secrets kept, lovers guided home. As the whispers grew, the moon felt herself again. She brightened, the hills sighed, and somewhere below, a traveler who had almost given up found the path glowing softly at his feet.
But what makes this really interesting is just the features. It's how all of this works under the hood. This level of speed, quality, and efficiency doesn't happen by accident. It's based on a new research approach that completely rethinks how AI generates audio. To understand why this works so well, and why it can run directly on your device, we need to step back and look at the research paper behind it.
Welcome back to The Explainer. So picture this. What if you could have the power of a high-end recording studio's AI, but right on your phone? That's what we're talking about today. There's this new tech called Calm, and it's promising incredibly realistic speech and music generated way more efficiently than anything we've seen before. Let's dive in and see how they pulled it off. All right, so first things first, how does an AI even listen to something? Well, it all starts with this, a sound wave. See how it's this smooth, continuous flowing thing? The problem is, computers, they don't do flow. They do numbers, ones and zeros. So the very first hurdle is always translation. You got to turn this beautiful, complex wave into a digital language that the AI can actually understand and work with. And that right there, that's the big problem, isn't it? I mean, we've all heard those amazing AI-generated songs or super realistic voices. But where do they come from? Almost always, they're being streamed from some massive, power-hungry data center. And why is that? It's because making audio that good has always taken an insane amount of computational horsepower. It's basically kept the best AI audio locked away in the cloud, totally out of reach for, the phone in your pocket or the laptop on your desk. Okay, so let's get into the quality versus speed dilemma. To really get why this has been such a tough nut to crack, we've got to look at how things have usually been done. For years, AI audio has been stuck in this fundamental trade-off, this bottleneck, where sound quality and processing speed are constantly fighting each other. It's all about thinking inside these little digital blocks.
So the old school approach is all about something called discrete audio tokens. And honestly, the best way to think about it is like trying to build a super detailed photograph, but you only have a small bucket of Lego bricks. You can kind of get the shape right, the basic idea, but you're going to lose all those subtle colors and fine lines. That's exactly what's happening here. The original smooth audio wave gets chopped up and squeezed into these digital blocks, and in that process, you lose information. It's gone forever.
Right. So you might be thinking, well, just use more Legos, tinier ones. And yeah, you could do that. In the AI audio world, that means using way, way more of these little tokens. And sure, the quality gets better, but the computational cost, it just goes through the roof. It explodes. And that is the trade-off. The exact reason why getting high-quality audio in real time on your own device has been basically a pipe dream. Well, until now. And this is where things get really cool. Let's talk about Calm, the continuous approach. The researchers behind this basically said, what if we stop using Legos? Instead of chopping up audio into these clunky, discrete blocks, Calm works with the data in its original, smooth, continuous form. It's like we're throwing out that limited box of Legos and picking up an infinite palette of paint instead. A total game changer. So how in the world do they do that? Well, the first key piece of the puzzle is something called a variational autoencoder, or a VAE for short. The best way to think of it is like a master artist. It learns how to listen to the original audio and then capture its absolute essence, all its important features as just a single point on this kind of abstract, high-dimensional map. That map is what we call the latent space. But here's the really crucial part. The VAE also learns how to do the reverse. It can pick any point on that map and perfectly reconstruct the original audio from it. That's the secret sauce. That's what gives Calm that infinite palette we were talking about. All right, so we've got our continuous data, our infinite paint palette. Now let's pop the hood and see how the Calm engine actually works. It's a really clever setup that manages to look at both the big picture and the tiny details at the same time, all to predict the next sound width, and this is the key: incredible efficiency. It really breaks down into 4 main steps. First, you've got that VAE encoder we just talked about. Its job is to turn the audio into that smooth data stream. Simple enough. Then, step 2 is the backbone transformer. Think of this as the long-range planner. It looks way back at the history of the audio to understand the big picture, like the overall melody of a song or the cadence of someone's voice. Step 3 is the short context transformer. This one zooms way in, looking at just the most recent super clean details to get things perfect. And then the final step, and this is really the magic trick. All that information from both the big picture and the close-up view gets fed into the consistency head. And its job? To predict the very next bit of sound in one single hyper-efficient shot. So here you can see the whole system working together. You've got the VAE doing its thing, encoding the audio. Then you see that long-term context coming from the backbone, giving it that sort of fuzzy, big-picture understanding. At the same time, the short context transformer is feeding it that super sharp, fine-grained info about what just happened. And they both come together, combine their knowledge, and hand it off to that incredibly fast consistency head, which then spits out the next sound. It's just a really elegant way to get both the context and the precision you need. And this quote from the paper, this is really the punchline. It says, Calm gets quality that's just as good as the best traditional models, but with just one step. Now, to really grasp how huge that is, you have to know how other models, like diffusion models, work. They start with random noise, and then they have to slowly, painstakingly refine it, sometimes over hundreds of steps, just to create a single sound. Calm does it in a single step. That's not just an improvement, that's a massive, monumental leap in efficiency. Okay, so the theory sounds amazing, right? But does it actually work in practice? Let's look at the payoff. We're going to put the theory to the test and look at the actual numbers to see just how much faster and better this new approach really is. All right, check this out. The numbers for speech generation are, well, they're pretty wild. If you compare Calm to a traditional block-based model, the RQ transformer, its sampler, that's the part that actually creates the sound, is more than 12 times faster. And it's not one of those things where you sacrifice quality for speed. Look at the human ratings. Real people listened to both and said Calm sounded significantly better. So it's a massive win-win, way faster and higher quality. And okay, if you thought that was good, look at the music results. It's even more staggering. The speed up here is a mind-blowing 19.3 times faster than the old Discrete model. I mean, think about that. That's not a small bump. That is a total game changer. It's a completely different league of efficiency. So this incredible efficiency, it's not just some number on a chart in a research paper. No, the team took this tech and they built something real with it. This is where we go from the lab to your laptop. They created an application called Pocket-TTS, and it is the ultimate proof of just how powerful Calm really is. And this right here is the whole point. Let's just let this sink in. We are talking about high-quality text-to-speech, running on your laptop, not on some server farm miles away, generating the audio faster than real time, faster than you can even listen to it. And maybe the most amazing part? It's doing it all on a regular old CPU, not a fancy, expensive, power-sucking GPU. This is it. This is the moment this tech breaks out of the data center and lands right on our own devices. And here's the hard data to back it all up. Look at a big, state-of-the-art model like DSM. It's huge, 750 million parameters, and nope, it can't run on a CPU. Now look at Pocket-TTS. It's a tiny fraction of the size, only 100 million parameters. It absolutely can't run on a CPU. And get this, despite being smaller and more efficient, it actually scored higher on audio quality. That LO score is basically a head-to-head comparison. So yeah, it's smaller, it's more efficient, it's more accessible, and it's just better. All right, so let's wrap this up with the key takeaways. The big problem was that the old, blocky, discrete models made you choose between quality and speed. You couldn't have both. The solution? Calm, which throws out the blocks and works with smooth, continuous data. The secret sauce, the innovation, is that amazing dual transformer design with the super efficient consistency head. And the real-world impact? This is huge. Powerful AI audio generation is finally free from the cloud and can run on the device right in front of you. And that really leaves us with one final exciting question. Now that this massive barrier, this need for huge, expensive computers has been completely shattered, what happens next? The possibilities are kind of endless, right? We're talking about real-time translation happening in your earbuds, video games with soundscapes that are unbelievably immersive and reactive, or powerful new accessibility tools that can change people's lives. So really, the question isn't if this tech is going to be everywhere. The question is, where are we going to hear it first?
Now that we understand the research behind this, let's see how it works in real code. Let's move into the code. Pocket-TTS, AI audio on your device. Imports and dependencies. Logging configuration. This function runs when the application starts and stops. When the server starts, it loads the text-to-speech model once and keeps it ready in memory. This avoids reloading the model for every request and makes the API much faster. When the server shuts down, the model is cleared from memory to free resources. This endpoint returns all supported voice names. It helps the front end know which voices are available so users can select a valid option. This also prevents invalid voice input from being sent to the API. This function converts text into speech using a predefined voice. First, it validates the input text and voice name. Then it uses the loaded text-to-speech model to generate audio. The generated audio is converted into a WAV file and returned directly to the user. This endpoint generates speech in the user's own voice. The user uploads a reference audio file along with text. The audio is first converted into a clean WAV format using FFmpeg. The model then extracts the voice characteristics and generates new speech using the same voice. Finally, the generated audio is returned as a WAV file. Temporary audio files are deleted after processing. This prevents disk space issues, protects user privacy, and keeps the server clean and secure. Thanks for watching. Please like and subscribe to our channel.